thank you for inviting me. And I'm going to start by apologizing that I will be staying just for my talk for lunch, and then I have to leave, much to my disappointment. Just busy time. So unfortunately, I won't have the chance to attend the other very interesting sounding talks of this workshop. So apologies, but you're recording everything, right? So maybe I can
most of the things. Yeah.
I can watch them later. I think it's an extremely interesting topic, and I'm also very pleased by the fact that you're bringing together people coming from different fields to talk about, so how do you do meta science if not in an interdisciplinary way, right? So that's really the way it should be. So I'm here as a philosopher, and also I'll be talking actually only about mathematics. And in this sense, it's different from most of the other talks that I've seen in the program, because most of the other talks are really about empirical sciences and how you gather data, et cetera, et cetera. And this is not probably not what's happening in theoretical mathematics. Of course, when you're doing applied mathematics, maybe there'll be more engagement with, let's say, the real world. But what I'm talking about here really is like, pure mathematics, theoretical mathematics. Okay, so the starting point is the idea that mathematics has this very strong collaborative component. This is something that is often overlooked, right? So we often have this idea, well, the empirical scientists, of course, they have to work in labs together, with big teams, like you think of the CERN in Switzerland and whatnot, whereas mathematicians can just like scribble stuff on the paper on their own, right? So it seems like, well, it's a solitary occupation. Well, it isn't, right? So there's a very strong collaborative component, social component in mathematics. And so this is basically how I approach the practice of mathematics. And one of the ways in which mathematicians collaborate is by actually being adversaries of one another. So by trying to spot mistakes in the work of their colleagues. And what I'll talk about today is this model that I've developed to capture what's going on in the practices of mathematical proof, called the Prover-Skeptic dialogues, and they're intended as a rational reconstruction of the practices of mathematical proof. And so basically this research finds itself in the field of what we call philosophy of mathematical practice, and also you could call it the social epistemology of mathematics. Okay? So all this is coming from this book that I published already now, almost 4 years ago. So it's old news in a sense. I think, Daniel, you know the book, right? So if everything is pretty much there, so you could just go, and it's in the last chapter of the book. Actually, the last chapter is about mathematical practice. It's actually also my favorite chapter of the book. So yeah,
might it have won an award? This book, maybe
it might have, but I'm not going to be advertising that.
Maybe the Lakatos Award, which is very, very nice. Yeah. Okay, no, just checking, just a question, clarification question. Thank you.
Interestingly, look who's the next on this next slide.
There you go.
And it's also for you, Daniel, because I know you're a big Popper fan, and Lakatos, at least, afterwards he turned against Popper, but what he wanted to do with proofs and refutations is really to transfer the Popperian idea of conjectures and refutations to mathematics. So at that stage, he really was a Popperian. And Lakatos is like this interesting figure because he had this tendency to kind of turn against his own fathers, his intellectual fathers. So the first one was Lukács when he was still in Hungary, who was like the Marxist philosopher. And then first Lakatos was kind of a Lukácsian as well, but eventually he turned against Lukács. And then he did a similar thing with Popper. I mean, this is just anecdotes, right, just to put things in perspective, but I think it's important as well. So this is one, proofs and refutations is amazing. I really love the book. I do, in my book, I do say, well, I'm very inspired by Lakatos, but my story, my model, my account is also different from his in many respects. I also just wrote a paper on this, so if people want to, just drop me a message and I can send you the draft. It hasn't appeared yet. But so in proofs and refutations, right, there's this, for those who don't know, it's this dialogue between a teacher and many students, and they're talking about Euler's conjecture that relates the vertices and faces and edges of polyhedra. And if there's this formula that describes how these three parts of a polyhedron, how they related to each other mathematically. So there's this conjecture, which was formulated by Euler, and then they go through the different proofs of the conjecture, and then every time somebody finds something wrong with it, and then they're like, oh, okay, so then we have to adjust. So the idea is that this dialogue really kind of reconstructs the history of these investigations on Euler's conjecture. And then at some point, one of the students says the following: that not only do refutations act as fermenting agents for proof analysis, but proof analysis may act as a fermenting agent for refutations. What an unholy alliance between seeming enemies. And so there's this idea on the one hand, it seems that, who's doing the proof is that, and then the other person trying to refute it, that they're somehow adversaries of each other, but in a way they're actually really collaborating. And that's pretty much the gist of what my story about these proof dialogues is about. So mathematical proof is a dialogical notion. This is something that I worked on for many years. I started working on this when I was first writing the VD. This was a VD project in 2010. So it's been a while. And the inspiration for this idea came from the history of logic, the history of mathematics, the Greeks, the usual suspects, right? So this idea that there's really this very strong dialogical component. Certainly, if you look at logic and philosophy, right, in the Greek period, but also in mathematics. So, Plato's dialogues and Aristotle's dialectic, right? So, for example, so there's the prior analytics by Aristotle is thought to be the first presentation of a formal logical system, syllogistic, right? So people love it, but what they don't, they read the first chapters where they're the formal proofs, and then after they're like, oh, look, great, formal proofs. The rest of the book is all about dialectic. It's all about these dialogical encounters of debate, right? And people tend to forget that. So that my whole, one of the goals of the project was to really kind of go back to, that's why it's called the Dialogical Roots of Deduction, right? To go back to these historical developments. And this, at the same time, this was happening in parallel with mathematics and Greek mathematics. And there's a very important book on this topic by Revionnet's. Book is now 25 years old and still the most comprehensive account of it's called The Shaping of Deduction. And so in this book, he says the following at some point towards the end. He says, Greek mathematics reflects the importance of persuasion. It reflects the role of orality in the use of formulae, in the structure of proofs. But this orality is regimented into a written form where vocabulary is limited. Presentations follow a relatively rigid pattern. It is at once oral and written. So this is really the key idea, that the slogan that summarizes the whole project is this one: it is at once oral and written. So on the one hand, you still see in mathematical proofs, you still see a lot of these dialogical features, as I will argue. I'll show you a bit more in a while. But it doesn't mean that it's all dialogical. Along the way, a lot of non-dialogical features, primarily pertaining to the written medium, have also been incorporated into these practices. Okay? So it's really this hybrid entity. So this leads me to this rational reconstruction, right? So proofs is how are they dialogical notions? So it starts with the idea that these dialogues are semi-adversarial, right? So they're not completely adversarial. They're more cooperative than adversarial. There's more cooperation than adversariality there. So we have two participants. Prover wants to establish the conclusion, and skeptic wants to ensure that the proof is correct and perspicuous. Right? So it's not that skeptic wants to refute the proof by all means, at all costs. No, skeptic just wants it to be a good proof. Right? Whereas prover does have a preference for the proof to go through. So in that sense, the interests are slightly misaligned, not completely, but slightly. There's a slight misalignment of interests. And that's why there's still a small adversarial component. But by and large, they're cooperating. And the dialogue starts, first with prover stating the theorem to be proved, and then asking skeptic to grant certain premises. And once skeptic does that, then prover puts forward all the statements, which prover says follow necessarily from what has already been granted. And what skeptic can do, the three main moves for skeptic are to present counterexamples. That's the traditional one. That's what you see a lot in Lakatos' book, Proofs and Refutations. But also, and this is kind of what I'm adding to the story, is also asking why questions. Ask like, how come, how's this, like, I don't get this step. This is going too quick for me, right? And this is important because this move is by and large cooperative, right? When the skeptic says, hey, sorry, but this step is not so clear, it's really a way to help prover to produce a more perspicuous, a clearer proof. That's in a way, that's really prover is being helped by skeptic. And the other move is, of course, granting premises at the beginning or not granting premises. These are the three moves available to skeptic. And this is, so in the book, I isolate three, what I call three cornerstones of deduction, or of, say, mathematical proofs. Three properties that these arguments have. The first one that's really exclusive to deductive arguments is the notion of necessary truth preservation, right? Which says, well, the argument really, like the conclusion has to be true in all of the situations where the premises are true. No exceptions allowed, none at all. And this idea is also that the argument has to be indefeasible. It cannot be defeated by the addition of incoming information. And this idea is captured quite nicely with the notion of adversariality, right? In the sense of like, I want to come up with an argument that is indefeasible, right? It cannot be defeated. And indeed, in all the dialogical accounts of logic by Paul Lawrenson and Jaakko Hintikka, they have emphasized very much this aspect. And then they developed the idea of a proof as a winning strategy, right? Using these game theory notions. Because in their conception, these dialogical these dialogues are zero-sum games, either one's going to win or the other, right? But for me, they're not zero-sum games, and these dialogues are not zero-sum games. So I cannot avail myself of the notion of a winning strategy as they can, but it's still fine because there's still this idea of an argument being unbeatable, and that is strategically a good thing for scale. Another property that is important to keep in mind is the idea of belief bracketing. I call it belief bracketing. And what this means is that you have to reason with the premises that you're given and nothing else, right? So not on the basis of your own beliefs about the premises and conclusions, right? So you bracket that, you put your own beliefs aside, right? And you can call this a hypothetical reasoning, right? That you're just like, okay. And this, one way to think about this is in terms of a perspective shift, right? So you should be able to reason also with the premises of somebody else, even if you don't endorse those premises. And this is not exclusive to deductive reasoning. For example, in a court of law, right? So say the prosecutor might do this too because the defense has granted certain premises, and then the prosecutor says, well, if you take these premises together, you get to some absurdity, right? So this is something that's done also not in other contexts, but it's important for deduction in particular. And in fact, my account of reduction absurdum proofs relies very much on this idea that there's a division of labor between the person who grants the premises and the other person who leads them to absurdity. So if people are interested, there's also a hyperperformance. And finally, there's the property of perspicuity, the property of that the proof has to be explanatory, at least preferably it is explanatory. And this is really the cooperative profile. This is really where you see that the proof is intended for people to really do something together, right, and understand the mathematical theorem on the question together. So this is too small, I know, but there's this tree of how the different moves relate to each other. So the graphic with the flow chart. So P first states the thesis, P is prover, and asks the skeptic to grant certain premises. If the skeptic doesn't want to grant those premises as well, they're not interesting, then that's it. Right? That's the end of that particular dialogue. But also if skeptic finds a global counterexample. Global counterexample, that's again a terminology from Lakatos, is a situation where the premises that the prover asked to grant obtain, and the conclusion does not. So immediately from the start, the proof is already due. Alternatively, skeptic grants the premises, and then the dialogue starts. And then first, prover goes to the first inferential step. And here again, there are three options for skeptic. If skeptic accepts that step, She doesn't have to do anything, maybe not. Yeah, okay, go on, prove. Another possibility is to ask a why question. So why? This step is not, it's not clear to me. Yeah, sorry. If the no move, then the dialogue simply continues. If there's a why question, then your prover has to clarify the step, maybe break it into two sub-steps. And that could also be a local counterexample. That particular step, right? So that there's a situation where the premises of that step are true, but the conclusion is not. And if this happens, then P has to withdraw that step or modify it, maybe introduce a lemma. I mean, a lot of the Lakatosian proofs and refutations dialogues are very much about this, how you have to do lemma accommodation. If this keeps going at the end, and then they arrive at the theorem stated at the beginning, then the proof has gone through. But it can also happen, of course, that there are so many objections, so many problems that eventually prover gives up on the proof. So now I'm actually moving to peer review. And there's this very nice work by Lina Anderson, who's a philosopher of mathematical practice. What she did in her PhD was to interview a lot of mathematicians on their refereeing practices. And what she found in how they, told her about their practices is that there's really, peer review is really very much a kind of dialogue. Right? So I met Lina many years ago, I think it was 2017. We met at a workshop. And we realized that, our results were really kind of converging. And then in this particular paper of hers, then she does refer to the Prover-Skeptic model that I was developing. So, we've been in touch since, but we came independently to this conclusion, right? And this is what she says. Contained in the published proof are the author's responses to the responses of this voice, and this voice is the voice of the referee that represents the sub-community, to the author. In this sense, the proof can be said to consist in a dialogue between the relevant community and the author. This suggests that we speak of a published mathematical proof as a piece of discourse with the relevant audience, not only as a piece of discourse aimed at that audience, right? So it's not just a kind of like rhetorical model where, there is an intended audience, that's the mathematical community, but the mathematician's just like putting it forward and it's received more or less passively by the audience. No. The idea here is that even how the proof comes about bears traces of this dialogue in the form of peer review. And of course, peer review, both informal peer review, right? So just talking to your colleagues and maybe, posting it somewhere in some, math overflow in some mathematical forum and getting feedback, but also formal peer review when there is a real, you send it to a journal and a referee, or of course you post it in the archive or whatever. But then there's formal peer review when it's really done by means of the request of an editor for a job. In both these cases, what typically happens is that the referee is asking these why questions, is making these suggestions, and this is incorporated into the proof typically, and then the end result, it bears traces of this conversation. And what Lina says, which I think was very, very interesting, is that the skeptic is checking for checkability. Right? What does this mean? What this means is that when the skeptic is checking the proof for correctness, she's not just adopting her own perspective, do I understand, but rather she's the representative of a community, of a research community, and so she's also interested in whether others will be able to, like from the same community with more or less the same background, will be able to go through the proof, right? So she doesn't only comment on the parts that she does not follow herself, but also the parts that she believes will be harder for others in the community to follow, okay? And so, because the expectation when a proof is produced, right, which is this kind of product for public consumption, is that the large majority of the experts in a specialized field should be able to validate the proof within a reasonable amount. If the condition is not satisfied, basically go back to the drawing board and find a better presentation of the proof, which will be digestible by at least the majority of your intended. Is that clear? So now I move to examples. How am I doing for time?
You have been talking for 20 minutes.
Okay, that's great. So I just want to I hope that's okay. I just want to ask if it's clear to everybody. Does anyone have clarificatory questions about the model so far? All right, because now I'm going to be applying the model. So it's important that everybody's on board. Yeah. You can be the skeptic to me, right? Like, sorry, it's not clear. Make it clear. So now I'm going to run through some case studies, which obviously is the kind of the most fun part. Some people say like this is doing kind of journalistic philosophy, you know, when you go look at the actual case. But I mean, really, we're people, right? So how do you do philosophy of science without looking at like these situations? So I'm going to start with an example from almost 100 years ago by now. It was Gödel's theorems, right? So Gödel's incompleteness results. Is everybody familiar with that? No? Okay, so what Godel proved is that you cannot, so before Godel, there was this other guy, David Hilbert, who was very optimistic about being able to prove the completeness of mathematics with mathematical means. What does completeness mean? Completeness means that every proposition that is true in that system can be proved to be true. So there's a distinction between being true and being provable. And Hilbert was very optimistic that it would be possible to prove with arithmetic the completeness of arithmetic. Philosophically, that's very interesting because that makes your mind kind of twist a bit, right? So that was the idea. And what Godel did was to prove that this could not be done with any system that contained a minimum amount of arithmetic. Okay, and this was this was very counterintuitive because Hilbert, it was known as Hilbert's program. It was very influential. And so this idea, this general optimistic stance, like we will, the slogan is, we will know, we must know. So it was a counterintuitive result. Just get some water here. Forget to get my water bottle. Leave it conveniently by the hands. Okay. So, in September 1930, Godel made the first public announcement of his incompleteness results. And interestingly, John von Neumann was one of the few who immediately understood. Do you know who John von Neumann is? I mean, big name, right? Game theory, physics, like, right? He, like, there's like this whole mythology around him, like he's the smartest guy of his period. So, von Neumann, in this case, again, he did his thing. He, in fact, Godel announced the first incompleteness results, and then von Neumann generalized to what later became known as the second incompleteness results, which are more, more general, like it's a broader claim. But, right, so, and also von Neumann saw immediately the far-reaching consequences of these results for Hilbert's program, and for this idea of investigating mathematics with mathematical tools, with mathematical concepts and means and techniques. So von Neumann understood immediately, but most people didn't. Most people thought, no, this can't be. It was a very surprising result because there really was this idea that it would be possible to prove every mathematical truth. Okay? And so, right, so many mathematicians were taken aback and they thought, no, there has to be a mistake somewhere in there. Right? This can't be. It's just too weird. And the results of the news of the results spread quickly, but obviously at the time there was no internet, or people couldn't communicate so easily. So a lot of the people didn't have access to the paper, right, to the details of the proof. They knew that there was this proof, but they couldn't see the details of it. There's this very nice paper by Paulo Mancoso on the background of the reduction of Gödel's incompleteness theorems. This is where I'm drawing from. And in particular, there's this one Polish mathematician. Do we have anyone from Poland in the room? Yeah, can you pronounce the Pristek? Yes, because I always ask before I butcher the name. So Leon Pristek, he thought, well, there has to be a mistake. And he was also, by the way, a painter. He's an interesting guy. So, but then afterwards, he wrote a letter to Kaufman, who was one of the members of the Young Service, also kind of an influential figure at the time. By the way, there's a self-portrait. He said the following: in my last letter, I have raised some doubts concerning Dr. Gödel's work that have completely disappeared after a more attentive study of the problem. I had at first thought that there was a tacit introduction, of non-predicative functions, which makes the use of a rigorous symbolical procedure impossible. And I even fear the possibility of an antinomy. An antinomy will be like a paradox. Right? And at the time, they already know about Russell's paradox, which basically destroyed Frege's logicist program. I don't know if anyone's interested in this. But so there was a recent event of something like of an antinomy that had been discovered, which had very far-reaching consequences. But then he actually read the whole proof and he said, now I see that this is out of the question. The method is truly wonderful and it fits pure type theory thoroughly. So what happened, right? So the result was surprising. So a lot of the people first were, hesitant to say, let themselves be convinced by it. But once they saw the details of the proof, everybody was convinced. Okay? Because in my terminology here, so this was an extremely perspicuous proof. It was very collaborative in the sense that the proof was detailed. And so anyone who had the chance to run through that proof immediately became convinced. Right? And no mistakes were found, and the results still stand. And, they're like one of the most important, right? Yeah, it's one of the most important results, mathematical results of the last century. I think probably the Turing results or the Turing machine results are even more important because basically they invented digital computation, but still these were very important. So fast forward quite a few decades. Now we go to 93, and this is the story of Andrew Wiles' proof of Fermat's last theorem. Apologies for I should have used Fermat's last theorem. Okay. So this was this theorem which had been formulated by Fermat, the mathematician Fermat, in the 18th century, and then he said, "Oh, I have a truly wonderful proof of this, but I don't have the space for it, so I'm not going to write it out." And then people spent centuries trying to find a proof of Fermat's last theorem. And the other thing about Fermat's last theorem, and sorry that I don't have there are, I think, enough mathematically minded people. The formulation of the theorem itself is extremely simple, right? It just uses kind of notions, arithmetical notions that even people in high school would understand. But proving it turns out to be very difficult. And so he made this astonishing announcement that he had proved Fermat's last theorem at a conference. And one of the times that I was talking about this recently was in the Collège de France in Paris on the invitation of Timothy Gowers, who's the mathematician, very distinguished mathematician. And I said, "Tim, you were there, right?" He was like, "Yeah, I was there." So it's really cool. And I'm talking about this. And somebody was actually in the audience and saw it happen, in real time. So there was this announcement. It was very bombastic, because people had been looking for a proof of Fermat's last theorem for centuries. So then Wiles submitted his 200-page proof. Right? It's a very complicated proof. And people are still trying to find simpler proofs of Fermat's last theorem. We can talk about it if people are interested. So he submitted this very big manuscript to the journal Illuminates Mathematica. And then the editors put up the proof among 6 referees. And one of them was this mathematician in principle, Nick Katz. By the way, an interesting feature of peer review in mathematics, maybe some of you already know, but I know many people are interested in peer review, is that it's not double anonymous. So usually the referee knows the identity of the author. Right? Not so much the other way around, but it can also be the other. Right? So that's certainly for philosophy, we're all very into triple anonymous, and I think it's a good practice, but it's an interesting sociological observation that that's not how it goes in mathematics. The other thing that's interesting about mathematics is that usually you only ask one referee, whereas certainly in philosophy you ask at least 2. I don't know about in psychology, it's usually 2, right? Yeah. So that's peer review mathematics is quite interesting. Anyway, so Nick Katz got a chunk of the proof, and then just to kind of spoiler, and I'll tell more details, he found a mistake. And it took Wiles a whole year to fix the mistake, together with another mathematician, Richard Penn. Okay? So and here's from one of those, public science magazines. Here's this very nice narration of this episode. So for 2 months, Katz and a French colleague, Luc Illuzi, scrutinized every logical step in Katz's section of the proof. From time to time, they would come across a line of reason they couldn't follow. Katz would email Wiles, who would provide a fix. Right? So this is the skeptic asking why questions. Right? So like, okay, I'm running through the proof. I don't understand this step here. What's going on? Note, by the way, notice that this was 93, 94, thereabouts. They were already emailing, right? And that's very different from the Godel story when there wasn't quick technology for communication. I'm also very interested in the history of the internet. So like different topic, sorry. But it's important because how mathematicians will communicate with each other and the technologies they have at their disposal will fundamentally shape how these interactions will take place. Okay. So, right. So he would find he couldn't follow a certain part of the proof. Cass would email Wiles, who would provide a fix. But in late August, Wiles offered an explanation that didn't satisfy the two reasons. And when Wiles took a closer look, he saw that Katz had found a crack in the mathematical scaffolding. At first, the repair seemed straightforward, but as Wiles picked at the crack, pieces of the structure began falling away. Very dramatic, right? And it took him a whole year to fix it. Okay? And I think this is like such a cool example of prover-skeptic interaction in real mathematics. That's really what was going on. And as you can see, the Illusian cats were really helping Wiles, right, to produce a better proof. In fact, the correct one, the previous one was not. So that's one story where there was a serious mistake found, right? Whereas with Godel, people thought there should be a mistake, but then there wasn't. Here, there was a mistake, but it was found and it was fixed. And now I'm going to tell a story of another surprising result, claimed result, which then turned out not to have such a happy ending. This is mathematician Edward Nelson in Princeton, who has, by now, in the meantime, he has also passed away, so he's not, I can speak of him in the past. But in September 2011, he was a very distinguished mathematician with a solid reputation. He announced that he had proved the inconsistency of Peano Arithmetic in the FOM mailing list, right? So this week, again, talking about the technologies for communication. There was this list for FOM, is Foundations of Mathematics. I was actually in this list for quite a few years, but it was, at some point, it was really nasty and unpleasant, like all those guys, showing who, okay, I'm going to say something vulgar, but who could piss further. So at some point, I just quit the list, but it was sociologically very interesting. And so, but anyway, so this is where he announced the results on this list, okay? And I don't know if you realize how mind-blowing this is, the inconsistency of Peano Arithmetic, right? So Godel had proved the incompleteness of arithmetic, right? So which means that you cannot prove every true statement, but inconsistency is if the system contains two contradictions that are both true, right? And if you use classical logic, this means the whole system explodes because then it trivializes them. So it's huge, right? It's pretty big and very surprising. Surprising, and it's huge and with very significant consequences. So it was quite bombastic, right, when this was announced. And then he provided two formulations of the proof, one in long book form, but also in a short summary, right? So they had two presentations. And immediately, of course, many people thought that had to be a mistake in the proof. Right? It would be very, very strange if arithmetic were inconsistent. It took only a few days for two people independently to find a loophole in the proof. One is Harry Tao, and the other is Daniel Stelsk, who was a mathematician in my alma mater, the University of São Paulo, curiously. Okay. And so they both found the same mistake. And they presented the mistake to Nelson right in the list, like, look, we think this doesn't work because this is the problem. And Nelson didn't immediately understand the objection, but then very quickly, in a matter of a few days, there was consensus that the mistake found was irreparable. So the proof could not be fixed. And then on October the 1st, so just a few days later, right, because it was September, and then on October, he acknowledged the correctness of the objections and withdrew the claim of having proved Nelson, of having proved the inconsistency of Peano Arithmetic. And so this was very graceful, but you can imagine for him, it must have been quite difficult. He had spent many, many years working on this. And then in a matter of a few days, the whole thing falls apart. So here's Tao writing on, because this is a blog post that I wrote like all the way at the time I was writing lots of blog posts, and he replied in my blog. So Tao was participating in the conversation, and then he replied to my question, like, how did you find the mistake? So what was the process? And he said the following. Actually, Nelson's proof was relatively easy to understand, in part because he took the trouble to write out a short outline which makes clear the general strategy of the proof while omitting most of the technical details, though it was ambiguous at one very crucial juncture. Right? So, Nelson was a very cooperative prover, had produced a very detailed, easy to check proof. And then he also said, aside from this one ambiguity, though, the outline was quite clear. Certainly, there have been other manuscripts claiming major results that were much more difficult to adjudicate because they were written so badly that there were no ambiguities or inaccuracies in the exposition, and any high-level perspective on the argument was obscured. So here you see, right, kudos to Nelson. He really produced a very perspicuous proof, one that was made it very easy for the skeptic to do their job to check the correctness of the proof. Okay, so this is also again very interesting how there's this interplay between cooperation and adversariality as it were. So now it's my last case. How much time?
So you have been talking for 36 minutes.
Okay, perfect. Yeah, so then I'll just take my time with the last case, and there'll be plenty of time for it. The last case is from around the same time. So this is a mathematician in Japan, Mochizuki. He, very distinguished too, has done a lot of great work before, so he has a very solid reputation in the field. And why am I saying this? Because, people announce groundbreaking results on a daily basis, but if they don't have the credentials, the community doesn't pay attention to them. Okay, and so it's not a coincidence that the examples that I'm mentioning are all of people with a high standing in the community. So actually, people bother to go through their results, right? And why is this important? And now I'm kind of digressing a bit, but it's important because in terms of workload management of the community. So going through the details of a mathematical proof is very time-consuming. Right? It takes a lot of energy and work. So people are going to allocate the time they have for this following certain criteria, right? And that means that they're not going to look into purported proofs if they don't have reason to think that there must be something in that, right? And this means that a lot of on a daily basis, people editors and journals receive proofs of a new proof of Fermat's last theorem in 3 pages, and they're like, okay, right? And these are known as the cranks, and there's a paper by a former postdoc of mine, Colin Rydberg, really interesting on justified exclusions in mathematics. So he argues there that it's not unfair that most of these results are not looked into from this workload management perspective. The community cannot afford to go through every single purported proof that is produced. Okay, but of course, this also opens up the space for prestige to play a role that can be complicated. So all the people I'm talking about here, they're all Cambridge, Princeton, right? Like all these fancy affiliations. Anyway, Mochizuki, on this, sorry for the digression, he was very distinguished, he's still, right? And he announced he had approved the ABC conjecture. The ABC conjecture is also a conjecture number theory that's easily stated, but difficult to prove. And also a lot of other results are implied by the ABC conjecture. So if you prove the ABC conjecture, there are a lot of other things that will follow from it, and that will be pretty major.
You cannot by any chance state it for us?
Yeah, I'll look it up, because the point is that you have to be quite precise on it, and I'm just afraid that I will not remember it. We can look it up when I'm done with the talk. I'll just.
It's called ABC conjecture. Yeah. It's not an abbreviation.
No. It has to do with the A, the B, and the C are variables. But yeah, I really don't want to kind of say, especially because I'm being filmed, I don't want to state it incorrectly. So let's just, when I'm done talking, we can just open the Wikipedia page, ABC conjecture.
You can't provide a short summary of the 500 pages. Are you sure?
So it was presented in this 501-page manuscript, which in turn was based on another manuscript that was also 500 pages long. Okay? Very complicated. And he had a very high reputation in the mathematical community on the one hand. On the other hand, he had been working in isolation for more than 10 years. So he had been working, developing his own new mathematical theory that that didn't kind of in isolation. So he didn't communicate this whole new mathematical world almost that he was developing to the community. Right? So that's why it was completely unknown. And so, because of his stature in the community, great efforts, also the importance of the ABC conjecture, great efforts were made to certify the proof. But most people, pretty much everybody just couldn't understand because the whole conceptual framework was so alien, right? It was so different. So there was a small number of mathematicians who studied intensely Mochizuki's work, who learned the framework, as it were, mostly close associates of his, right? Mostly in Japan, not all of them, but most of them are also in Japan. And they affirmed very emphatically that the proof is correct. They claim they have certified it. But, so for years, but it was a very limited number of people. And for years, the proof was in limbo because most mathematicians could not be convinced by it. But they could also not find a mistake, right? In the other cases we discussed, the mistake was found and pointed that, look, this is where the problem is. And then, either it was fixed or it wasn't fixed, but there was agreement on where the problem is. Here, not. And here's a statement by a mathematician, Emerson, who says, no expert who claims to understand the arguments has succeeded in explaining them to any of the very many experts who remain mystified. And one of the big questions here is who counts as the right expert? Who counts as the right skeptic, right? So if you think that the expert should be any, professional number theorist, that's a broader range of relevant experts, most of them are mystified. But Mochizuki says, no, the only experts are the ones who really took the trouble of learning my theory, of learning the whole mathematical background that I developed. They are the true experts, and these people have already certified their proof. This is why there was this limbo situation, because it looked like there was actually a disagreement on what counts as the relevant expert. Okay? So this went on. There was the stalemate for a while, and then in 2018, two mathematicians, Peter Schulze, who was also Fields medalist, and Jakob Stix, also very respected number theorists, they thought they found a mistake, and then they went to Japan to discuss with Mochizuki because Mochizuki refused to travel. So it's like, no, you want to talk to something. So they went to Japan to discuss what they thought was a fatal mistake involved. Okay, and then this is again from those popular science articles. There's the following description of what happened. But the meeting led to an oddly unsatisfying conclusion. Mochizuki could not convince Schulze that his argument was sound, but they couldn't convince him that it was unsound. So still stalemate, right? So it's still not clear whether the argument has a problem, right? This 3.12, or if it's just the receivers, the skeptics, who are failing to see that the proof is actually correct. So there's really this thought that this is where the cooperative interaction between proof-skeptics is kind of breaking down, right? And it's not clear. So Mochizuki thinks that the skeptics are not sufficiently cooperative because they don't take the trouble of learning the theory on which his proof is based. But the community, by and large, thinks that Mochizuki is not a sufficiently cooperative prover because he didn't take the trouble of formulating his results in a language that most of the people in the community could understand. So it's still stalemate. I haven't heard anything new in the meantime, so I think we're still in this position. The proof has been published, but in a journal where Mochizuki is one of the editors. So how much this really, so it's just an interesting case where it seems that, the Prover-Skeptic model, it's not that the model breaks down. In fact, it it illustrates, right? It illuminates when this interaction can break down itself. All right, so that's these are the cases. And now just to conclude, so spotting mistakes is at the very heart of the production of mathematical knowledge. This is an insight that already comes from Lakatos, and later work in the philosophy of mathematical practice has shown that, and work on peer review mathematics is very interesting for that. And the interesting thing is that mistaken proofs can also lead to new mathematical knowledge, right? So there are examples of these proofs that are failed proofs for the result that they intended to prove, but they introduce this amazing new technique that then just completely, is very revolutionary for other applications. And that's, by the way, also an idea from Lakatos. Lakatos, in fact, doesn't think that the purpose of proofs is to establish a conclusion, right? To establish a theorem. He thinks that it's about giving rise to new concepts and techniques. It's much more this kind of creative idea. And this model, the Prover-Skeptic model that I developed, is an attempt to capture the interplay between adversariality and cooperation in these practices. That's this to explain. And also to highlight the fact that mathematics is an inherently social epistemic practice. And you see this in particular in the interactions between prover-skeptics, right? So between, in processes of peer review, both formal and informal. Okay, so that's why mistakes are good, right? In mathematics, that's where new mathematical knowledge comes from. Yeah.